Hello and welcome back to my channel. Many engineers design a voltage mode buck converter using a PI or Type 2 compensator, and then wonder why the loop suddenly becomes unstable when they try to increase the bandwidth. In this video, I will explain why that happens and why a Type 3 compensator is usually required when designing voltage mode controlled buck converters. The reason comes directly from the power stage dynamics of the buck converter and the limitations of simpler compensators. Here is what we will cover in this lesson. First, we will look at the frequency domain stability metrics, crossover, phase margin, and gain margin, and how they determine stability. Then we will connect these to the time domain behavior, where we define overshoot, undershoot, and settling time on a real transient example. Next, we will briefly explain why a compensator is needed in voltage mode control and why the raw plant cannot regulate by itself. We will also compare different types of controllers and see why PI and Type 2 compensators are not sufficient for voltage mode buck converters. Finally, we will show why the Type 3 compensator is the correct and standard choice, and this will prepare us for the practical Type 3 design workflow in the next lesson. Here is typical loop gain plot of a well-designed buck converter. Let's review the three main stability metrics. The crossover frequency is the point where the loop gain crosses 0 decibels. This defines the bandwidth of the closed loop system. In other words, how fast the converter can react to disturbances. The phase margin is the distance to minus 180 degrees phase at the crossover point. It tells us how stable the system is. A higher phase margin means smoother settling, less overshoot, less ringing, more robust to parameter variations. A very low phase margin means overshoot, oscillations, and sometimes even instability. The gain margin tells us how much plant gain could increase before the converter becomes unstable. In practice, gain margin is less important than phase margin for everyday design, but it still gives us insight into robustness. If the phase never reaches minus 180 degrees at any frequency, the gain margin is considered infinite, which is the case for our buck converter loop gain example. That simply means that increasing the loop gain will always cause the crossover to happen at some lower frequency where the phase is still safe. In practice, infinite gain margin just means the limiting factor is phase margin and not gain margin. If the loop phase crossed minus 180 degrees as indicated in the figure, the gain margin would be the vertical distance between the magnitude plot and 0 dB at that frequency. In this hypothetical case, our example would have a gain margin of approximately 55 decibels. These metrics determine the whole dynamic behavior. A higher crossover means faster reaction, smaller voltage dip during a load step, and shorter settling time. But if the phase margin is too low, the converter will overshoot, ring, or even oscillate. So we have a fundamental trade-off. Higher speed is equal to lower stability unless we add enough phase boost. That's why compensator design is all about reaching a stable crossover with enough margin. Now let's look at the time domain view of stability. This is a switching simulation example that helps us define the performance metrics. Overshoot is the amount by which the output voltage rises above its nominal value after a load decrease. Undershoot is the amount by which the output drops below its nominal value after a sudden increase in load. Settling time is the time required for the output voltage to return and stay within a small tolerance band, usually plus minus 1% or plus minus 2% of the target voltage. In the example shown here, the overshoot after the load decrease is about 100 to 200 millivolts. The undershoot after the load increase is around 150 to 250 millivolts, and the settling time for both events is roughly 300 to 400 microseconds. These values are typical for a stable, well-designed Type 3 compensated buck converter operating with a crossover in the tens of kilohertz range. These measurements gives us the time domain interpretation of the stability concepts we saw in the body diagram. The relationship between frequency and time domain is very direct. A higher crossover leads to faster correction and shorter settling time, but a lower phase margin increases overshoot and ringing. A higher phase margin gives smoother behavior but slower response. So the transient behavior you see here is the time domain expression of the crossover frequency and phase margin we discussed on the previous slide. The buck converter has a strong LC double pole in its planned transfer function. This creates almost minus 180 degrees of phase lag near the resonant frequency. Without compensation, any attempt to push the crossover frequency higher leads to very low phase margin and instability. Also, the raw plant has no integrator, so it cannot regulate the output voltage. The output drops under load. A compensator is therefore required to provide DC regulation, shift the crossover frequency, boost the phase margin, and ensure good dynamic performance. This is why closed loop voltage mode control cannot work without a compensator. Before we move to the Type 3 compensator, let's briefly look at why other controllers do not work for voltage mode control. A P controller has no integrator. That means it cannot remove steady state error. The output voltage will always drop under load unless the gain is extremely high. But high gain pushes the crossover near the LC double pole, where the phase is already near minus 180 degrees, causing instability. Also, a P controller adds no phase boost, so it cannot stabilize the system at practical bandwidths. A PI compensator improves DC accuracy by adding an integrator, but it still does not shape the phase. The LC double pole still gives minus 180 degrees of phase lag. If we try to make the loop fast, the phase margin collapses and the crossover becomes unstable. A type 2 compensator adds 1 0 and introduces some phase boost, but not enough to overcome the LC double pole in voltage mode control. Type 2 can work for current mode control because the plant is effectively single pole, but in voltage mode the phase deficit is too large. As a result, the crossover frequency must be kept low, which limits transient performance. So PI and Type 2 simply cannot provide the combination of high crossover, strong phase margin, and fast transient performance that we want. A Type 3 compensator is specifically designed to solve the voltage mode buck converter problem. First, it provides roughly 90 degrees of phase boost, which is exactly the amount we need to offset the minus 180 degrees phase lag from the LC double pole. This let us place the crossover frequency much higher while maintaining strong phase margin. Second, the two zeros in the Type 3 compensator can be positioned to partially cancel or counteract the LC double pole behavior, giving the loop a much better phase profile around crossover. Third, the two high frequency poles help roll off noise and push down the gain at frequencies where switching noise and measurement noise dominate. The integrator ensures zero steady state error, giving accurate output voltage regulation. Together, these features allows a Type 3 compensated voltage mode buck converter to achieve fast, stable and well-damped transient performance at practical bandwidths such as 5 kHz, 10 kHz or higher. For these reasons, Type 3 is the industry standard choice for voltage mode control buck converters. This concludes our introduction to stability metrics and the motivation behind Type 3 compensation. We now understand how crossover, phase margin, and gain margin define stability, how these metrics shape the transient response, why compensation is required, why PI and Type 2 cannot handle the LC double pole, and why Type 3 is the right choice for fast, stable voltage mode control. If you want to learn how to design a Type 3 compensator step by step, including automated design in Octave, loop gain verification, LT-SPICE simulations, and firmware implementation on TI-C2000, you can find the full voltage mode buck converter course linked in the description below. The course takes you from small signal modeling all the way to full digital implementation on real hardware. If this video helped you understand the topic, consider subscribing for more digital power electronics content. Thank you for watching, and I will see you in the next video.